Welcome back. Today we have a little hard-turning project. These parts were done by somebody else in a soft condition. I think they were run on a CNC lathe, and then they were vacuum hardened and tempered. That means no scaling, only a little bit of discoloration. Very good dimensional accuracy after hardening. This surface, this and the ID of the board, those are critical. And we will also skim cut the OD here and cut a nice large chamfer on here as stated in the drawing. And there are also two holes missing because of an error in the communication, let's call it that. And there is also another detail that I want to go in with a part like this. It's turned from C45 steel, that's 0.45% carbon, a medium carbon steel, and hardened to about 55 Rockwell C. You can even see this one that I already stoned on the face. Here you can see the mark from the diamond cone to check the hardness on the part. We need to make one, but as these parts were run on a CNC lathe, they decided to make like 4. So why not? So when you work with parts that have been hardened and need to be machined, you need to think about your order of operations, what you use as a reference. In this case it's a little bit easier because due to the vacuum harden, the dimensional accuracy of the part is still quite good. It's not warped beyond crazy. Okay, let's look at the drawings. What I like to do when I work with parts that have allowance on them, I mark out where to machine them. Otherwise you lose track of what you're doing. Basically the complete OD contour and 2 of the faces here need to be machined. The thread is finished, no need to do anything about it. The ID needs to be finished, and I think we will, this is wrong, we'll leave the floor of the floor surface of the bore alone. But I marked something back here. This is a chamfer, and somebody forgot to draw a center line here. Okay, now it's better. We need a chamfer back here, and the reason for that is that's important. That's really important. Let's do a quick sketch. Okay, we draw a cross section of a part with a countersink. And we don't forget the center line. Got a proper sketch for a rotational feature needs a center line. Then we draw a screw in here. The screw is of course a little bit smaller because you drill for clearance. Then we have a head. The head is of course shallower than the counterbore. Then we have a line here. That's the edge of the bore top. And the screw of course has a line here. Okay, that's our screw inside a counterbore. The problem is, a screw doesn't have a perfect 90-degree angle in here. There is always something like this. Screws always have a little bit of radius here, and if you try to force that into a sharp edge on the counterbore, the screw will not seat correctly. This part will try to center on this radius, kind of half-assed, which you absolutely do not want when you do a counterbore. With a counterbore you want to have a little bit of side-to-side room. Otherwise you could just use a countersink, a conical head. And for that reason, you always, when you counterbore a part, you always put a countersink here. Not much, maybe 0.2 millimeters or something like that. Just a little bit of a chamfer. Let's make it red. Always. And to show that this is not something stupid, or that this is real, let's look at this part. It doesn't have a countersink in there. Let's check the bore diameter, or the hole diameter. 4.2, this is clearance for an M4 screw. And when we take a standard DIN 912 screw, that's the standard, the old standard for socket head cap screws here in Germany, and we measure the OD of the thread. That's all hunky-dory. 3.84. That's a lot of clearance in the screw and the whole loop. But when we measure the same very much up on the head here, 4.4, 4.38. That's a problem. We could force the screw in there, we could tighten it down like mad, but the problem is it's just not right. It damages the section of the screw here. The part doesn't really orientate, it wants to center itself on this radius. It's just bad practice, so we need to put a little bit of a countersink on there. Basically a better edge break. So that's that. And let's first talk about our order of operations. So what I was thinking, what was I thinking? We're going to clamp this part on here, turn the OD, face it, chamfer it, turn the ID. The ID is very critical. And then we'll make a stub arbor with a short centering register that goes into the freshly bored ID and has a face contact too. Primarily face contact, but also a centering boss for runout. And then we just need to turn the OD here. Roll on the lathe, and the part will go straight in the 6-jaw chuck. No other prep work needed. And during clamping, I spin it back and forth a little bit, maybe an 1/8 of a turn, just to feel if it seats properly in the jaws, or if it's a little bit crooked, which is unlikely with that diameter to length ratio. But still, in my mind, it's good practice. You feel if there is something wrong. Give it a light grunt. Don't bear down on it, otherwise you collapse the bore in here. Then you bore it to your perfect tolerance. You loosen the chuck end. Your bore is oversized. Oh, now we bring in a dial test indicator. Okay, that's a run out. That's well within maybe 4 microns. A little bit of distortion on the shape, obviously, because it's jumping very weirdly. Let's see if we can adjust that out. That's better. I really love this lathe. For a heavy-duty hobby lathe, this thing is really spot on. And no, this is no joke. The indicator really makes contact with the part here. It is what it is. Vacuum harden is really a very precise process. Doesn't move the part. What I did to adjust my runout here is, this is an adjustable chuck, It has 4 set screws back here. What I did to adjust the runout is, this is an adjustable 6-jaw chuck, not an independent jaw chuck. That's nonsense. You have 4 set screws back here, and these are used to shift the whole chuck with the part clamped on the back plate. And this is definitely the superior way compared to any other non-collet work holding methods on a lathe. That's very universal. Note that I didn't say the best. There is no the best. But for a universal chuck, that's one of the best. And it's super fast, way faster than fooling around with a 4-jaw independent. We're at my slow speed grinder, which I have a separate video on, and I have a CCMT insert tool holder here with a CBN carbide insert. This is a used insert, well used. You could use it for some turning, but not for what we want to do today. So we're going to bring this back to life, make it a very, very usable tool. The table of the grinder is tilted away from the wheel about 5 degrees. And I will bring my tool into contact like this, but also tilted maybe 5 degrees this way. That way we grind on the lower corner of the insert. The lapping wheel will spin this direction, so we grind into the cutting edge. We add a little bit of spray lubricant. Otherwise, these wheels, these are super, super fine diamond wheels. Otherwise, these tend to load up. Okay, that's all we need. The red line I put on here, this is just for me as a reference if I have to come back to the lapping machine and give this another quick lick on the diamond lap. That's the facet we lapped onto this CBN tool, and this has now a razor sharp edge and really an excellent finish on here. And that's all that's needed to bring a used CBN that's at the end of its lifespan, doomed to be a roughing insert. That's all that's needed to bring it back to life and make it a super, super valuable tool. If you keep your eyes open on eBay, you can find boxes full of CBN inserts for like $5. Note that I left the radius here intact. This helps to give a very, very good surface finish. If you can lap this to a dead sharp edge too, to a dead sharp corner, but that has its impact on the surface finish. The radius kind of scallops the finish a little bit and helps with a nicer finish. We start by turning the OD to 24.5 millimeters. And I negotiated some slightly looser tolerances than what the print states. We're going for plus 6 microns on the OD in this case, plus 6 micron on the bore and minus 6 on the OD on the other end, just to make it a little bit more realistic. The tool we lapped cuts beautiful. Keep in mind this is 55 Rockwell, a decent hardness. Now we take our digital micrometer, we check our zero, and this is not good. Let's take a piece of paper and clean out the anvils of the micrometer. Just a regular piece of note paper. Pull it out, try again, and now we have a repeatable 0. Yeah, repeatable within a few micron. So now we take a measurement. Note that that this is a cool new item. This is a Mitutoyo Quantum mic, and the nice thing about these is one rotation on the thimble resembles 2 millimeters of motion on the anvil here. So going from very small to very large is a breeze, super fast. And they do not have the small ratchet thimble back here, but the whole drum here is a ratchet. This is really a crazy repeal and crazy accurate instrument. It's almost obscene that I can own something this precise in a home shop. We remove a bulk of material now, like 0.2 millimeters in one pass, something like 1500 RPM. That's fun, when the chip wraps around the part. Not critical in this case, because it's away from the surface we're working, but still rather annoying. I take one pass now, do a measurement, and then take my final pass. So this should be 24.55. It's 24.56. That can happen because the tool either wears, or if my center height is not exactly correct, the diameter is not a linear function when you move in. So we will adjust for that. I just entered that number into the DRO. Now we adjust and we turn. And now, most likely, this should be around 24.5 millimeters, give or take. It's 24.505, so plus 5 micron. With a that sharp lapped CBN tool, we could take a spring pass and bring it down another few microns, but I think we'll leave it like that. Now we need to face. There is no critical dimension about that, we'll just take a facing pass. This is just necessary to clean up the end. Now for the most tricky part on this part, the ID. For the hard turning, we're going to use the CCMT boring bar with another relapped CBN insert held in a split block in a standard multifix block. Now this is not hardened, this is just heat blued, kinda. We take a first light pass just to get a known dimension. It wants to chatter a little bit, but usually that goes away once the bore gets larger. Most of the squeaking and chatter has gone away. We are 0.2 millimeters away from our target dimension, and the surface finish is always going to be quite nice that way. So let's go to 10.9 millimeters and leave us 0.1 to do our balanced cut and finish dimension. Let's check our internal dimension. This is clearly a case where you want to use something like a 3-point internal micrometer or something better, not telescoping gauges. This is clearly not the right application for them. So we are 20 microns below the dimension I'm shooting for. I was shooting for, so 120 to go. So I'm shooting with 20 micron increments for my final dimension. Yes, I'm sneaking up to the final dimension, but that's only possible in this case because the tool I'm using creates very, very little cutting pressure. And even a spring pass, which still takes some material off despite the very low cutting pressure, even the spring pass is extremely controllable and reliable. Okay, spring pass, just to be sure. The bore finish is just a thing of beauty. That's substantially better than anything I could achieve with a tool post grinder to do ID grinding. This is like 4 micron oversize. Gets a little bit smaller the farther you go in the bore. This is like +1 micron. The part that goes in there is not that long. The bore is deeper than the part long. Also, for double checking, I have a pin that's 10.996. That's a high-speed steel punch that I mic'd carefully and rounded the end over with a stone in a lathe. And this is just a nice idiot check. Yeah, putting something in the hole is always pretty good double check. We don't need a super defined chamfer on the edge of the bore. I'm just using the boring bar and the angle to put a nice lead-in chamfer on there. Chamfering leaves a secondary burr, both on this edge here on the outside and on the inside. So here's a round stone, and it will just work both edges very lightly, very little pressure, and kind of roll them over a little bit. I think that's an aluminum oxide stone, but it doesn't really matter for this application. That's a nice deep earth chamfer. Now for the large 3mm chamfer, we will step turn it down, and then we will take a full plunge cut to clean up the chamfer. This should work kinda okay-ish. It's probably not going to be the nicest operation here. You see me working down in diameter just until my chamfer cleans up. Yeah, this last cut was not necessary, but we will spare ourselves the heavy plunge cut to clean up the chamfer as it's just a chamfer. We're going to take some 3 micron lapping film and give it a quick wipe down with it. That should give us a nice finish. We have no cheddar marks, so that's good. So oh, this blows out the camera. So this stuff is 3 micron aluminum oxide lapping film. I think 3M makes that stuff. It's a plastic carrier with aluminum oxide grit, 3 micron on it, and it's adhesive backed, so that's super useful. I usually stick it on a ground surface, on a ground parallel, and use it like that for cleaning up surfaces. But first we need to get rid of those chips, because I will be very close with my fingers, and I don't want to tear off my fingers on these chips, because that hurts. Pair of tweezers. Tweezers are like heavy-duty fingers. When you don't want to ruin your real fingers, use tweezers. Book. There we go. So here's the lapping film. Yeah, that cleans up very nicely. The stuff tends to load up. A little bit of cutting oil helps usually. So that's a pretty decent finish. And the geometry of the part is basically untouched from the lapping film. Part can now come out of the chuck. That's a pretty okay finish. I'm not going to complain about this. Remember what I said earlier about the chamfer on the bore, or on the hole on the inside of a counter bore? That needs to be chamfered. We could put it in a lathe and use an internal chamfering tool to put a little chamfer on there, or do it like this. That's a trick I think I saw Robin do this at one point. This is not a countersink, this is a ball carbide burr. This is what you would normally use in a die grinder. But these work exceptionally well to deburr holes with a cordless drill, especially in hard and hardened materials like hardened steel. We can put a tiny chamfer on this side too. And the trick is to choose a size of burr where you end up with something that resembles the rough shape of a 45-degree chamfer. It's not a 45-degree chamfer, of course. It has a spherical shape, but it's more than adequate for what we need here. And it looks very clean, it's round, and it's quick. So, cordless drill. Best machinist friend. For our next step, we need a little fixture. I have a piece of, this is probably free cutting mild steel, and it already has conveniently a M4 thread in the end. Exactly what we need. This goes in the chuck. Run out doesn't matter at all. We will make it run out. Or no run out. We will turn a registered diameter on this part. That's a little bit smaller than the bore on the part. Okay, this is strictly a caliper dimension. So 30 microns undersized. Doesn't matter, because we're going to bolt this part on here with a long 4mm screw and torque it down nicely. This already gives a very, very good registration, even as the centering boss on the arbor is a little bit undersized. But this being an adjustable 6-jaw chuck, the next step is very easy. We will bring an indicator in. I was asked if I still use my shop-built solid indicator stand, and well, yeah, I do. And also, I still use this eye poker stick on top of the tool post to mount it with our magnet base. This back here is just my camera holder. This is a super, super solid way to mount an indicator on a lathe. Once again, Robin Renzetti's idea. That's where I saw it first. So I'm choosing this camera angle because I want you to be able to see the indicator and me adjusting the 6-jaw chuck for runout. We spin it around and we watch the needle of the indicator. This is low spot, this is high spot, this is about 30 microns in between. So we go to a low spot around here, and conveniently we have already a set screw here, and we will split the difference, so we will raise it about 15 micron. Like this. And I always back off the screw once I move the jaw, because when I go to the other side, I don't want to fight the set screw. And you can see that we're already we're already pretty darn good. That's 2 micron. That's an honest 2 micron. Let's sneak it up a little bit. Usually you make it worse once you get that close. Or you make it better. But this is a point where the 2 micron indicator starts to fail. We would need to put an electronic indicator or something more sensitive on here. This probably was too much. Nope, that was perfect. That's right on. We don't touch it anymore. We don't talk about it. That's some darn good run out for you. Maybe the width of the needle. And yes, the indicator is making contact. Back to the CBN OD turning tool. What we're going to do, we turn this OD here to 14 millimeters minus 6 micron at max. A little bit awkward to measure because I want you to see it on camera. And that's 13.997 for you. But that's okay for a hobby lathe, really. I'm not complaining at all. This is within tolerance. Second to last step is a facing cut here. go. Nice shiny finish there. So shiny. Really, last step is a shallow lead-in chamfer on the cylindrical part here. That cut didn't behave very well for some or another reason, but that's okay. This is just a lead-in chamfer. We need to polish the end anyway. Okay, I also stoned this corner here, this edge, so it's a tiny radius, no burrs anywhere. The thread was turned with a full profile insert, so root and crest of the thread is very nicely machined. No need to do anything there. We can pull the part off and call it done. Blink. Comes off like this. Many years ago, this would definitely be work for a cylindrical grinder, not for a lathe. But these days, with ceramics and CBN tooling, hard turning like this is a breeze. Okay, ceramic tools are around forever. But ceramic tools seem to need a lot of cutting pressure to work actually, compared to CBN, which just, depending on the geometry it's ground to, works exceptionally well with very low cutting pressure. So that's bushing. Okay, over on the milling machine using a 1.5mm 2-flute carbide end mill. And I'm drilling the 2 holes to tighten the bushing down with a spanner wrench. And I'm packing very slowly, about 20 to 40 microns per pack, to get to final depth. I do that by watching the DRO. You can see that I always retract about 200 micron, go back, and then go down a little bit more. And this is what it looks like on the fine feed hand wheel on the quill. It's just back and forth until we're at final depth. And here you see what the bushing is for. This is used to mount a big Kaiser boring head in a number 30 taper holder that goes in a jig borer. The boring head goes in the bushing, gets tightened down with a screw, and then the whole assembly gets screwed into this tool holder. One might argue that this part does not need to be that accurate. And that's kind of true, because it's a single point boring operation when you use a boring head. But I know the person who this is for, and he is one of the 1000% type guys. The part has to be spot on, even if it's not entirely necessary. And I'm happy to deliver that. So here again, picture of the final part. Looks quite nice. For video purposes, I machined 2 of them. So don't be surprised. Not everything can be done via the magic of video. So I hope you enjoyed this. Thank you all for watching. Thanks for the ongoing support. Stay safe and stay out of trouble. See you next time.